In this video, we'll look at the concept of epsilon-nets. Consider a set system defined by a ground set X and a set of subsets of X, S. A subset N of X is an epsilon-net if the following holds. It basically means that if we have large subset, such as S, then S must include some element from the epsilon-net. In other words, the epsilon-net hits or includes an element from all the subsets of X that have more than epsilon fraction of elements in them. For example, if X is this and the set system is defined like this, then the subset 2 and 4 is a 1/2 net. There are two subsets here that have at least half of the elements of X, and this includes one element from each subset, and thus 2 and 4 is a 1/2 net. First, we'll prove a basic bound that is in fact tight as long as we don't have any structure on the set system. The theorem says that for a given set system, there always exists an epsilon-net that has roughly this size. We prove it using a probabilistic argument. We pick P to be a parameter, that is a probability, and then we sample each element with probability P in N. In other words, we include every element of X in N with probability P and exclude it with probability 1 minus P. Let's look at a fixed subset S inside a set system. What is the probability that we do not sample any of the elements in S? Since our sampling is independent, this probability is obviously 1 minus P to the number of elements in S. By doing some calculation, you can easily see that this is at most e to the minus P times size of S. Now we plug in our parameters. Imagine S is big. Then we put this value for the probability. If we do the calculation, it follows that this probability is smaller than 1/the size or than the size of the set system. Now we use the union bound. The union bound officially says the following, that the probability that one of the two events happens is at most bounded by the probability that the first event happens plus the probability that the second event happens. By simple equations, such as the probability of an event happening plus the probability of an event not happening always equals 1, we can work out the union bound to give you the following. If the probability of an event is at least 1 minus something, then the probability that k such events happen simultaneously is at least 1 minus sum of this value. So in this case, the probability will be at least 1 minus k/4 times s. However, we know that the set system has at most s subsets that are large. In other words, in our set system, k is at most size of s. This means with probability 3/4, our sample will be an epsilon-net. We are not completely done yet. We need to look at the size of the epsilon-net. The size of the epsilon-net, or the expected size of epsilon-net, is this much. This is because each element of X is sampled with probability P. By plugging the values, we get that the expected size is this much. This means with probability at least 3/4, we're not going to have too many elements in our sample. In other words, the number of elements in our sample will be at most some linear factor times this value, which is exactly as we claimed. Now let's look at a better bound. In this better bound, we assume some structure. We assume the set system has VC dimension D. And we would like to prove that we have an epsilon-net whose size is independent of the size of the set system. It only depends on the dimension and the epsilon. So if the dimension and epsilon are both constant, then the epsilon-net has also constant size. The proof is slightly more complicated. I will set the parameter P to be this value. You will see the reason later. We do twice of the same kind of sampling. First, we sample every element with probability p in some set n1, then we do it again. Obviously, the expected size of each of these subsets are the same, and they're both, the expected size is d over epsilon times log of d over epsilon. Okay, from now on, I will assume the following simplifying assumption. I'm going to assume that the size of the set system is m, and all of the possible subsets in S have size at least epsilon times size of x. In other words, I will ignore the small subsets because they do not matter. I look at two events. The first event is the event where my first sample n1 fails. This means there exists some subset in S that has no element in n1. In other words, n1 is not an epsilon net. The second event is an event when F happens, so the first event happens, and on top of that, the subset that had no element in n1 suddenly has many elements in n2. Obviously, F prime is a rarer event than F. In other words, for F prime to happen, F must happen, and on top of that, something else must also happen. So the probability of F1 is at most, or smaller, it is smaller than the probability of F. However, the probability of F cannot be too much larger than the probability of F prime. In fact, we would like to say that the probability of F prime is at most half of the probability of F. In other words, 2 times probability of F prime is larger or equal than the probability of F. This is because our two samples are independent. N1 and N2 are two independent samples. Consider some subset S that does not include an element from N1. What is the probability that we include more than this many elements in N2? That probability is obviously constant. In fact, you can show that it's at least 1 over 2. So with probability 1 over 2, the subset S that makes N1 fail will on average have this many elements in N2, and thus you can show that this part of the probability event happens with probability 1 over 2. Thus we have the following inequality. Now let's look at a different way of considering these two samples. Let n be the union of these two samples. What does event f prime mean? Event f prime means the following, that there exists some subset in S such that there are k elements of it sampled in set n, and all of those elements come from N2. But we can look at n in the following way. We can consider n to be a sample where we have sampled each element of x with probability roughly 2 times p. The exact value of the probability will not be 2 times p, but it is very close to 2 times p, and you can easily figure it out by solving a quadratic equation. This is true because N1 and N2 are two independent samples. So for some element to be included in N, it has to be either sampled in N1 and N2. For an element to be excluded from N, it has to fail to be sampled in N1, and it has to fail to be sampled in N2. By doing some relatively easy calculations, we can show that N can be thought of a sample where each point in X is sampled with some probability that is very close to 2 times p. So with this view of N, how can we look at N1? We can look at N1 in the following way. We can look at it as first sampling a subset N, and then assigning each X to N1 with probability roughly 1 over 2. So for every X that is sampled in N, we decide with some probability that is very close to 1 over 2 whether or not to assign it to N1. Now we go back to the proof. The main point where we're going to use the bound on VC dimension is the following. that we can restrict our set system to n, and we can only look at the subsets inside this restriction. This is because the part of the subsets that are outside n do not matter, because what we care about is the intersection of the subsets with sets n1 and n2. And since we want to bound the probability of f prime, we only need to look at subsets that have at least k points in n. So what is the probability of f prime happening? The probability of f prime happening is the existence of some set S that does not have any element in n1, but it has k elements from n. If you look at n1 in the following sense, then it follows that this probability for this particular S is at most 2 to the minus k. In other words, S has k elements from n, and all of these k elements must be assigned to k2. Must be assigned to n2. This means this probability is going to be 2 to the minus k. Since this probability of 1 over 2 is approximate, we're going to have O notation here. Now, if you use the union bound, it follows that the probability of f prime happening is bounded by this. Since the number of elements in the restriction of S onto n is going to be bounded by the VC dimension, we can get the following, that the probability of f prime happening is bounded by the size of n to the d times this 2 to the minus k. If we plug in the value for k from this equality, you can see that it simplifies to 1 over 4. So with probability at least 3 over 4, f prime fails. In other words, f prime does not happen. This means f does not happen, which means our sample will be an epsilon net. With probability 3 over 4, our sample will have size bounded by its expected value, and thus similar to the previous case, we have proved the existence of an epsilon net that has this size.